This lesson is going to take you through a curve sketching example. Specifically, it is going to be an example using a polynomial function, and we're going to make use of the function, its first derivative and its second derivative, to make the most accurate sketch that we can. So the example we're going to use today is f of x is negative 3x cubed, subtract 2x squared plus 5x. And we're going to start by analyzing the function f of x without considering its derivative. So what can we determine just based on the function that you can see here? So we're using our previous knowledge, and this is kind of part of the algorithm that we're going to do for any function. We're always going to start by considering the function itself. What do we know about the function that we're seeing? So in this case, you should be able to see that the domain is going to be all real numbers, right? There are no discontinuities in this function since it's polynomial. And then we want to think about the fact that we could consider the intercepts. And also, of course, you can consider end behaviors. So we're going to start with intercepts. And of course, you can determine here that the y-intercept is 0. And that's going to be confirmed by the fact that we can factor out the negative x. So f of x is negative x times 3x squared plus 2x minus 5. So we get a factor times a quadratic. And it does also turn out that this is factorable. We get 3x plus 5 and x minus 1. So we now know a few things. We know that it goes through 0. And sorry, I really should finish this. So if we want to find intercepts, we set it equal to 0. So x is 0, negative 5/3, and 1. And as we go through this process, you're encouraged to put as much of the sketch onto the grid as you can, and then we will just continue to add to it. So let's use, I should put a scale on here too. So okay, we've got another intercept at 1 and one at negative 5/3. So that's a little less than negative 2 by 1/3 of the box. And that's going to start to kind of guide our shape here. We also know that because it has a leading coefficient that's negative, that the end behaviors should look something like this. And we're going to try to figure out as much as we can about what happens in between those points. So now we're going to consider the first derivative. So there we have the first derivative. And of course we care about the critical numbers here because we want to look at increasing and decreasing intervals. So we're going to, again, set this equal to 0 because the derivative will never be undefined. So the only points we need to worry about are when it is 0. And we should also find that this is factorable. So the derivative is 0 at 5/9 and -1. And we could, of course, complete a chart to show ourselves increasing, decreasing intervals, but we already basically have the ability to make those estimates because we know that it has a negative leading coefficient, so we know what that cubic's going to look like. We just now have the actual points where our local mins and maxes are going to occur. So we need to consider where f at 5/9 is going to lie. And it will turn out to be approximately 1.6. And we can do these pieces in approximates because we're going to then plot them on our functions, and there's no way we can be that accurate in a sketch anyway. So using approximates with 1 decimal place for this purpose is fine. And this one gives us -4. So that gives me 2 more points that I can plot. 5/9 is approximately 0.6. So at 0.6 and 1/6, we know we're going to get a local max. Sorry, 1.6. And at -1, -4, we're going to get a local minimum. Now we're going to consider the second derivative. So again, this is part of our algorithm. We start with f at x and we work our way towards the second derivative. And here we get that that will be a line. And of course, our second derivative, we can use these values to double check and determine for sure that these are local mins and maxes that we got before. So we can consider that f double prime at 5/9, which will give us -14, so that's less than 0, which makes sense because that one turned out to be a local maximum, right? So it's occurring on an interval that is concave down. And f double prime at -1 will turn out to be 14, which is greater than 0, which again makes sense. We predicted that this should be a local minimum. And we know that it's decreasing from -infinity to -1. It's increasing from -1 to 0.6, and then decreasing from 0.6 to infinity. And we know that there's going to be a point of inflection, or at least we think there is going to be. There is a point here for the second derivative that is 0. And that second derivative is 0 when x is 4/18, in other words, 2/9. So we know that there's a potential change for the concavity there. And so we're going to just double check using our interval chart. Sorry, that should be -2/9. So we're going to split up our interval at -2/9 here. And that means we can test with -1, which will make this positive. So this is concave up. And so we can test the right side of the interval with 0, and that'll be negative. So it's concave down. So now we feel definitely pretty confident here that there's a point of inflection at -2/9. So we want to know where that point really is. And it'll turn out to be at approximately negative 1.2. So that gives us one more point that we can use. So negative approximately 0.2 and negative 1.2. So we got there. It's going to be our point of inflection. I really should label that point outside of where I know that drawing is going to be, and we'll just use an arrow to show where that point of inflection is. Okay. I can sketch my curve there, going through all of my known points, and feel like it's a nice, pretty accurate sketch. There we go.